So welcome to the seminar today. And our speaker today is Yiming Chen, and he's from Princeton. And he will be talking about his new work on understanding the spectral factor from enlarged limit in string theory and these theories. Okay, so maybe people can mute themselves if you are not speaking because there's some feedback here and there. Thanks. If you okay, yeah, over to you, Yiming. You can you can start your seminar.
Let me share my slides. Okay, thanks a lot for the invitation, for letting me to speak. And today I will be talking about this recent paper that I just wrote, in which I investigated the property of the spectral form factor for two simple quantum mechanical systems. One is free large and gauge theory, and the other is strings. So basically, in this talk, I want to first begin with a bit of motivation and discuss why I'm interested in this problem. Of course, the motivation of studying the spectral form factor really comes from some questions when thinking about black holes. But then I will turn to these simple systems and see how we can solve some puzzles in this about black holes in these simple systems. Of course, these simple systems are very different from the black hole. So I will talk about how they are indirectly related to black holes and how we can push the results in my discussion further to try to understand black holes. And in the end, I will give some discussion. So I will be mostly focused on the string case because the story is easier to understand there. And for the gauge theory case, I will mostly by drawing some analogy between strings and gauge theory, try to give you some basic results. Okay. So the spectral form factor is a useful quantity that you can define in general in a quantum mechanical system to diagnose the fine-grained feature of the spectrum. So the usual way that people define it is to define it as the square of the analytically continued partition function. So usually the partition function is a sum over e to the minus beta times the energy, but you analytically continue the beta to beta plus it and square it. So as you increase t, as you fix beta and increase t, this quantity can probe finer and finer detail in your spectrum. So in recent years, people have applied this quantity to study the black hole physics, either in low-dimensional quantum gravity, such as the JT gravity, or in a toy model of holography, such as the SYK model. So in these models, there are some distinct features of this spectral form factor. So for example, in this picture, I'm showing you a plot from a paper by Schenker and Stanford, where they studied this spectral form factor for the SYK model, which is a 0+1 dimensional quantum mechanical system that shares many properties with the black holes. And there are three regimes of the spectral form factor that is usually talked about. So initially, as you increase t, since now there are these, now all the energy eigenstates do not just contribute real numbers, they contribute some phases, so they start to cancel out each other. So initially this quantity decays, and it decays smoothly. So that is usually called the slope. And this short time decay is governed simply by the continuous density of state. Okay. Then at a much later time, this quantity starts rising again. And in this picture, there are two curves. One is a black curve, and the other is the red curve. So the black curve is the answer that you average over many individual quantum mechanical systems, while the red curve is, for example, you take a particular realization of the SYK model. So you see that for a single realization, the curve fluctuates a lot, while if you average it, you get a smooth linear growth, which is called the RAM. So people have understood pretty well the reason that you have a RAM. So that is a universal property whenever you have a random matrix statistics in your spectrum. Okay. Well, at a very, very long time, this quantity eventually saturate, the average of this quantity eventually saturate at some constant value. And that is related to the fact that the spectrum is discrete. So if you average the square over a very long period of time, you should get a finite number. This quantity is also useful to consider because it is a very natural quantity to compute in gravity. So it's very a natural quantity to consider in the context of holographic duality. So for example, usually when we do holography and we compute the partition function, analytically continue the partition function, we will just fix the boundary length of the space-time to be proportional to beta plus IT, and find the bulk saddle point, smooth bulk saddle point that fills in that boundary, okay? And we know that if we consider this quantity for the black hole, for t equals to 0, it's just given by the Euclidean black hole saddle point, where the thermal circle shrinks to a point at the horizon. Now, this still holds when you go to beta plus IT. So semi-classically, the bulk calculation is still given by the black hole saddle point, at least at short time. But it's some analytically continued black hole saddle point, and it's a complex metric. Now, in JT gravity that is dual to the matrix example, it was understood what the bulk correspondence of the ramp is. So in the last slide, I was talking about the bulk correspondence of the short time behavior that is given by the black hole saddle point. While as pointed out by Sachenker and Stanford, the long time behavior, the ramp, corresponds to a space-time wormhole. At least this is pretty well understood in the context of JT gravity. Sorry. Excuse me. Okay. Yeah. So, but the inclusion of wormholes in the gravitational path integral has led to interesting puzzles, because if we just have a holographic system that is dual to a particular Hamiltonian, it's difficult to interpret the connected contribution of two partition functions. So I think you probably have already heard about this puzzle. So let me not go into detail of that now. And another puzzle is that in a system that is dual to a specific quantum mechanical system, we expect an erratic curve like this red curve here. So what gives rise to that curve? And what is the bulk mechanism for that? And if there is a bulk mechanism for producing this erratic curve, what will be the role of the wormhole? Okay. However, in this talk, I will not really be talking about the ramp, because as I said, in this talk, I will be talking about theories that are much simpler. For example, the free large-N gauge theory and strings. There are systems that are nearly integrable when you have a little bit of interaction. So at least at short time, you won't never find the random matrix statistics in your spectrum, and you shouldn't expect there is a ramp. But we will be interested in another property of the spectrum, that is the discreteness, which is there even for integrable systems, okay? Usually this is attributed to the plateau at a very late time. But now let me tell you, there is another version of the spectral form factor where the problem of discreteness starts to come in at a much earlier time, and actually at a time that is of order 1. So to really tell you about that, I need to make an important digression, okay? So basically, we will be considering a different version of the spectral form factor that is like a micro-canonical version of the spectral form factor rather than the canonical ensemble version of the spectral form factor that I showed you earlier. So this spectral form factor I denoted by the Y quantity, and it is given again by the sum over energy eigenstate, but with Gaussian window around some center energy E and some width delta, okay? So you sum over state with this Gaussian envelope, and it picks up contribution around this center energy E. So this seems like a much more complicated quantity to consider. So why do we even bother talking about this? There are actually a few very good reasons to consider this quantity rather than the canonical ensemble one. So let me tell you about them. The first reason is that if you consider this quantity Z of beta plus IT, for an ADS structural black hole in high dimensions, there is a Hawking-Page transition as you increase t. Namely, at t equals to 0, the answer of this quantity is dominated by the black hole saddle point. But at some t of order beta, the answer will rather be dominated by the thermal ADS saddle. So if you just naively consider this quantity, you cannot really focus on the black hole states for a long period of time. To see this, basically, the argument is very simple. We know that there is a Hawking-Page transition on the real axis of beta. So now the question is simply, how does that phase transition get extended into the complex plane of beta? And as you do that exercise, the answer is that the phase transition happens at some t of order beta. So there is another closely related reason that you don't want to consider the canonical ensemble partition spectral form factor. So the reason is based on the recently proposed Kontsevich-Siegel criterion for complex metrics. So if you have never heard of it, this is a criterion that proposed by Kontsevich and Siegel and further developed by Ed Wheaton. It's a way that they propose to diagnose whether a complex metric is a sensible metric to include in the gravitational path integral or not. Okay, and as I alluded to earlier, as you fix the boundary length of the space-time to be beta plus IT, this metric in general is a complex metric. And it is not just that the time has a complex period, because you need to ensure that the horizon is smooth, that the geometry is smooth at the horizon. The structural radius also has to be a complex number. So this metric will be a complex metric, and you can use their criteria to see whether this metric is so-called allowable or not. So just based on this criteria, you also see that this complex metric becomes unallowed also at a very short time, at a time that is of order beta. These two facts have a very interesting connection that you can check that the thermal ADS saddle always dominates over the black hole before the black hole becomes unallowed. So which is a check that this allowability criterion really makes sense in this case, because as it becomes subdominant, it becomes unallowable. On the other hand, if we consider—
Can I ask what exactly this criterion is?
I'm not sure. Yeah, it's basically, I'm not sure I'm giving you the detail here, but basically is that if you have a diagonal metric, you look at the faces of each element of each diagonal elements. So for example, a Euclidean metric will have faces will all be 0 because all the diagonal element of the metric is real. But now the metric is complex, so the faces are not real. And the criteria proposed in their paper is that the sum of the absolute value of all the faces have to be smaller than some number. So basically the metric cannot be too complex, like the faces cannot be too large. And this criterion is derived by analyzing the perturbative quantum fields on the space-time. Basically what they argued is that when the faces become large, the fluctuation of quantum fields around your saddle point can become unbounded from below. So at the basic level, you think that this semi-classical computation becomes untrustworthy. So that's the basic idea. Okay. Okay, so if you consider this microcanonical ensemble quantity stays allowable rather than this canonical ensemble quantity. So this slide is basically telling you that in order to focus on the black hole states at a much longer time scale, we wish to focus on use this microcanonical ensemble quantity. Now,
okay, can
another benefit, yes?
Can I ask one question about this criteria? So this criteria one has to check at all points in the space-time, or how?
Exactly.
Yeah.
Exactly, and this violation at t of order beta mostly come from the property near the horizon. So it's pretty universal. It applies for flat space black hole, ADS black hole, all kinds of black holes.
Thanks.
Does that answer your question?
Yeah.
Okay. So there is a third benefit of this Y quantity, which is actually more important for my discussion. And the property is that it decays very fast at short time. So since it decays very fast at short time, it makes it much easier to expose other possible contribution to the spectral form factor. If it decays much slower, it will just hide all the non-productively small corrections. But since this quantity decays very fast, it's easier to see what happens at later time. And to see that it decays very fast, let's just consider a very simple toy example. Let's say that the density of state is almost flat, okay? Then as an approximation, as a short time approximation, we can replace this discrete sum by a continuous integral over the energy, replaced by integral over this density of state. And let's say the density of state is a constant. Then this expression is nothing but the Fourier transform of a Gaussian function, right? Of a Gaussian window function. And we know that the Fourier transform of Gaussian function is still a Gaussian function. So you see that y square in this toy example decays as some constant e to the 2s, e to the 2 times entropy, which is just the density of state square, minus delta square t square. Now, this tells you that it decays exponentially with respect to t square. And for a black hole in ADS, it's convenient to choose delta to scale as order 1 over square root of G Newton, because this is a natural choice, because that is the energy fluctuation that you will have in a thermal ensemble. Okay, and if you use this choice, you see that all the terms in the exponent scale as 1 over G Newton. For example, the entropy, of course, is of order 1 over G Newton. That means that this quantity decays to exponentially small at a time that is order 1 in the Newton's constant. Now, in this talk, I will be plotting the logarithm of y squared rather than y squared. So if you plot the logarithm, it will just be a curve that crosses 0. And when it crosses 0, it means that y squared becomes exponentially small, namely of order, sorry, there is something wrong with my mouse, but hopefully I can continue. Okay, so when it crosses 0, it becomes of order e to the minus 1 over G Newton. And now, this is the answer that you will get if you consider a black hole. If you do a semi-classical computation of using the black hole, compute this y quantity of the black hole. But this gives you the wrong answer as long as after it crosses 0, for a very simple reason. We need to be reminded that the y quantity that we begin with is a discrete sum. And it is a sum over exponentially many terms. Each term contributes an order 1 number. So unless miracle happens, it is unbelievable that this quantity becomes exponentially small, right? It's unbelievable that order 1 term sum to an exponentially small number. Of course, there can be special spectrum that have special property that can have this property. But in general, what we learned from recent years is that black hole is supposed to be some very chaotic many-body quantum system. And at a very finer scale, the spectrum pretty much should look like a random matrix. And there is no reason to expect such miracle to happen. So we don't expect this black hole setup point to give the right answer forever, and something should replace it. And as I have already mentioned, that was as was proposed by Sachin and Stanford, there can be a wormhole setup point that comes in and give you an order 1 but rising answer. But here another surprise is that it seems that to save this problem of decaying to exponentially small, the wormhole will have to come in at a very early time, at an order 1 time. So the question that I want to propose about the black hole is that whether there is some other phase in between, or does the black hole just immediately go to the wormhole? of course, as I mentioned earlier, the understanding of wormhole is not very clear, in particular in higher dimensional gravity. Now, let me turn to what I will actually talk about in this talk. That is, we will analyze the spectral form factor in some simpler systems, including free large gauge theory and gas of strings. So this.
Yiming, can I ask something
yes.
also?
Yes.
Is there only one single wormhole geometry, or there can be also complex wormholes, just like you can have a complex black hole saddle?
Right. So basically, as proposed by Sachenker and Stanford, there is only one wormhole geometry, but it has a free parameter that is like the width of the wormhole or the minimal geodesic of the wormhole. And that parameter increases as you increase time. So there is a one parameter family of wormhole. Does that answer your question?
Yes, so that leads to this rise that
yeah, that leads to that rise.
But I was saying that is it known that there could not be any other saddles, like other complex saddles?
No, it's not known. And the property that we will see in this very simple model is, of course, we don't have wormhole in these simple systems because we don't have random matrix statistic. But what replaces the black hole is some other saddle points that share some property with the black hole, which is the focus of my talk. So I will be talking about that.
Okay.
But of course, for the black hole, we don't know whether other saddles exist. Maybe we are missing something, or maybe there's some reason that they don't exist.
Okay. So they're still disconnected geometries.
Yeah, disconnected geometries. Exactly. You can say that.
Oh.
So these are simple. The large and free gauge theory and gas of string. There are simple systems that, in principle, we know the microstates, at least in the free limit. And in the end, we surely won't find a problem with discreteness. We can just plug in the eigenstates in the computer and generate a spectral form factor. So what are we supposed to learn from this? The interesting perspective of these systems is that we could phrase the question of computing the spectral form factor in terms of quantities that have some geometrical flavor. So in terms of things that are analogous to the black hole, while the discreteness of the spectrum will not be manifest in this way of thinking about the problem. And I will make this precise later. The focus will now be what are the new geometries that come in to solve the problem of the decay of the spectral form factor. Of course, one should keep in mind that these systems have a spectrum that is very different from the black hole. So the lessons that we learn from them cannot be directly applied to the black hole. But nonetheless, I will make some comments about how one could attempt to understand better the black hole problem from this angle. So now let me start to talk about a gas of string, and in particular, what do I mean by geometries for a gas of string? The question is very physical. Let me emphasize this point. We are just considering fundamental strings in string theory. So take some Lorentzian space-time, put a gas of string in your Lorentzian space-time. Maybe it has some weak gravity interaction, and maybe it does not. So I will be considering both cases. But the problem that we are considering is just to consider the spectral form factor of this string gas, okay? It has some discrete eigenvalues, and we want to consider spectral form factor. But another way of thinking about the same system is not to really think about it in the Lorentzian spacetime, but rather than thinking about the strings on a thermal manifold. So this is an interesting point in string theory that has been appreciated by many people. That just as usual, when we think about thermal physics, we can consider the theory on a cylinder. So the time is compactified in the Euclidean circle with length beta, inverse temperature. Here I'm drawing as a cylinder, so there is also some transverse space, which I will just take to be flat space, okay? And the analog of geometries in this case are various string winding modes on the thermal manifold. So something about string theory is that whenever you put it on a cylinder, the string has the property of, possibility of winding on the thermal circle. So you can have a string that winds once, winds twice, etc. The string can also move along the thermal circle. So that is momentum along the thermal circle. And there are many string modes once you consider this manifold. So the most famous string mode is the so-called thermal scalar. So it is a string mode that winds the Euclidean circle once, or a -1, that means winds in a different direction once, and has no momentum. Okay, so this is a often discussed string mode on this kind of manifold. And the reason that it is interesting is because people have understood that this the existence of this string mode is directly tied to the high energy density of state of a highly excited string gas. So an interesting result of a highly excited string gas is that at high energy, the density of state grows exponentially. So it grows as e to the some number times the energy. And this number is the so-called inverse Hexagon temperature, okay? And this behavior is tied to this thermal scalar, because the thermal scalar on this manifold becomes massless exactly at when beta approaches the inverse Hexagon temperature, beta Hexagon. Okay, and now basically what I'm saying is that this thermal scalar is closely tied to this continuous density of state. And if you just consider the continuous density of state and plug that into the formula of the spectral form factor, since it's continuous, it just gives you an ever decaying curve, decays forever and decays to exponentially small at a time that is of order 1. Okay. So we will basically, the point will now be studying what are the other string modes, what are the other things that will contribute to the spectral form factor, that will save the decay of the spectral form factor. But at this stage, I have to
can I ask something here?
Yes, please.
So this particular growth leads to another feature also, right? That there is some particular scale, or which is given by the Hexagon temperature. Above the scale, you cannot really have an effective local effective theory. The effective theory is typically non-local.
Yes.
So does that, but is that crucial, or you simply need to say that you want to say this particular form, or what exactly is relevant for this decay?
Yeah, that is not very important for my discussion here, because I will be always working in the microcanonical example. So I fix the energy. I never fix for example, I don't fix the temperature to be higher than the Hexagon temperature. I fix the energy. And the microcanonical example of strings is well defined for relatively low energies, as long as the string does not collapse into a black hole. So that's basically the answer. For high enough energy, of course, the microcanonical example should be dominated by black holes, but I will be considering relatively low energy. So we don't need to worry about that aspect.
Okay.
Okay, but at this stage, this identification of geometry and the winding mode, I have to admit, is very vague. However, there is a literal connection that was pointed out by Horowitz and Polchinski. So let's consider a gas of string in 3+1 dimensions, and the rest of the dimensions are compatified to a string scale. So once we include a little bit of gravity attraction, the gravity is just slightly strong enough to pull different parts of this string gas together to form a dense object, an object that is like a star made of strings. And what Horowitz Polchinski did in this beautiful paper in 1997 is that they used a condensate solution for this winding mode chi, a Euclidean condensate solution, to describe the thermodynamics of physically a string star in the Lorentzian signature. And let me call this solution the Horowitz-Polchinski solution. It is a classical solution of the equations of motions of string theory. And conceptually, it is very similar to the black hole. Namely, if you compute the entropy of this solution using the Gibbons-Hawking procedure, you get the correct entropy as you would expect for a string gas. So that is similar for a black hole. We could compute the entropy of the black hole using the same procedure. While also, it's similar to the black hole in the sense that it doesn't give you the microstates, and it doesn't tell you that the spectrum is discrete. Okay, so we have this problem for the black hole, as I mentioned earlier. So the upshot is that basically, if you, rather than considering the black hole, if you consider the Horowitz opportunity solution, you get a similar curve, and it decays forever. So
again, so I don't understand this statement, this solution. So, how do you compute the entropy of the solution? Does it have a horizon?
It doesn't have a horizon, but still, yeah, still it has an entropy because. So this was discussed in a paper last year by me, Huang, and Edward. So basically, the Lagrangian of this winding mode action in this winding mode action, there is an explicit dependence on beta because the mass of this winding mode depends on the temperature. So that explicit dependence will give you a classical entropy, and that entropy is also of order 1 over G Newton, just like the black hole. So it is some classical solution. You can use the Gibbons-Hawking procedure to compute the entropy. Maybe your question is, we're not computing the entropy using the area formula. By Gibbons-Hawking procedure, I'm talking about you compute the partition function and you vary the length of the thermal circle a little bit and take derivative, stuff like that. Does that answer your question?
Okay.
So you can go through this procedure and give you some entropy, which is exactly the entropy you expect for a string star. But of course, here I'm
the crucial thing that you're saying that it's a Euclidean, it's a well-defined Euclidean standard.
Yeah, it's a well-defined Euclidean saddle, just like
which has a Lorentzian analog also, and
yeah, exactly. Yeah,
okay.
exactly.
And
it gives you correct entropy, coarse grain entropy for the Lorentzian thing, but as you extend to longer time, you see a problem of it, just like you see a problem for the black hole. You see that it starts to give you a wrong answer. So something else has to save you, okay? Now, this question I first heard from Stephen Schenker in a talk, during a talk, and he was asking, now, in this case, can we understand what we have to add to the Horowitz opportunity solution in order to save the decay of the spectral form factor, or in order to get an answer that is that respects discreteness of the spectrum?
Yeah. Can I ask something about the Horowitz-Polchinski solution?
Yes, please.
So the solution is a Euclidean solution. You mentioned that it has a Lorentzian version. Is the Lorentzian version like a real solution, or is a complex? What is the?
What I meant that it has a Lorentzian. I'm not saying that there is a classical solution in the Lorentzian signature that I know of. What I was saying is that it described the physics. This Euclidean solution described the physics of a string gas in the Lorentzian signature. But I'm not sure whether there is a good way to use classical solutions to describe that string gas directly in the Lorentzian signature.
Yeah. Okay. And is the Euclidean solution real, or that also has complex numbers in the metric?
So this is completely real at t equals to 0. So in the usual thermodynamic discussion, you never have complex metrics. But now, as you go to this spectral form factor, as you increase t, it will be slightly complex. But the situation here is better than the black hole in some sense. It's less complex in the black hole. So I don't think in this case it will be unallowed under the criteria.
Okay.
Does that answer your question?
Yeah, it does. Yeah.
Okay, thanks. Thanks for the question. Okay, so now let me try to solve this problem finally.
Sorry, one more question. And the Euclidean circle never shrinks to 0 size in the Horowitz-Polchinski because, as you said, the solution doesn't have a horizon.
Yeah. Mm-hmm.
So yeah, okay.
Yes, exactly. There's a difference from the black hole.
Yeah.
But in terms of this conceptual discussion, that difference doesn't seem to play an important role here.
Yeah. So this is like beta del beta kind of the entropy will come from when you take this logarithmic derivative kind of thing, roughly.
What exactly do you mean logarithmic derivative?
No, I mean you are saying that. So if we follow the Euclidean quantum gravity prescription for calculating the entropy, the metric depend in some way on beta, such that when you take the relevant derivatives, the entropy will come out to be non-zero.
Right.
correct way of thinking.
Here it mostly comes from the action of the winding mode, not directly of the Einstein-Hilbert action. So, but the idea is what you have in mind. You do the same calculation as you do for the black hole, but rather than getting an area term, you get this integral of the winding mode. So the final result is different, but the procedure is the same. Okay, so let me try to tell you what really happens. So as I said, the Horowitz-Pochinski solution is a solution with a little bit of gravity interaction. We don't really, in the Lorentz signature, once you have a little bit of interaction, the spectrum of a highly excited string gas will be much more complicated than the free case. And we don't have a good way to solve that. We could try to solve that in perturbation theory, but no one has done that.
I don't understand your statement, this phrase. What do you mean by little bit of interaction? Because it's a mass, so you cannot switch it off. It is they have particular masses, so you cannot control the interaction, right? What do you mean by how can you control?
I mean the Newton's constant. Or the string coupling.
But the masses also scale with the same Newton. No, they don't. Okay, they scale with alpha prime. And
the mass of the mass of the Horowitz-Pochinski solution is of order 1 over G string. That's why the gravity attraction is important in this solution. So here, let me try to maybe focus on lower energies, and so the gravity attraction is unimportant. Or let me or you can fix the energy and take the string coupling to 0, then you won't have this solution anymore anyway, because the existence of the Horowitz-Pochinski solution requires a little bit of gravity attraction.
Now, so I was saying that in what is the limit that you're taking, like string length versus Planck length kind of thing, in which limit that's
Yeah, here let me take a limit where the Planck length goes to 0 while the string length stays finite.
I see. Okay, thank you.
So the reason that I want to discuss this first is because this is very easy, and because we know the spectrum of free string. So in principle, you could just try to plug the spectrum into the computer and see what the spectral form factor look like, and try to come up with a theory of that. Okay. So of course, one can try to do that a numerical exercise, and what you see is that you get at early time. So here I'm plotting the spectral form factor for a single highly excited string, but there's a reason that a single highly excited string is basically the same as many little strings. And at early time, you see this decay that is exactly what you predicted from this winding mode argument. This is given by this continuous Hexagon density of state, but it doesn't really decay forever. At some time that is of order alpha prime, square root alpha prime string length, it starts to bend over. Okay, and it starts to bend over, and it has a linear growth in this curve. So of course, let me emphasize this. This will not be linear in the. This is not a linear growth in the spectral form factor, because here I'm plotting log y as a function of t. Okay, so if you plot log y as a function of log t, it will not be linear. So it's actually an exponential growth, but it's a very slow exponential growth compared to the initial decay. And if you zoom in into the detail of the spectral form factor, you actually see these bumps, and these bumps are one after the other, and the separation between them gets smaller and smaller as you go to later time. Now, what we want to explain is what is the physical mechanism for the rise and this detailed feature of the spectral form factor. Of course, you can say that this is just a consequence of the spectrum. Well, we'll plug the spectrum into the computer, we get this. There's no more thing to say about that. But here I'm trying to explain that from the other angle. Namely, we know the string mode that is responsible for the initial decay, that is the first winding mode. Now we want to know what is the string mode that becomes responsible for the other ones. Okay. Now to solve this problem, I need to digress a little bit to talk a little bit about free string partition function. So there are some property of the free string partition function that is very useful to capture what is important in the spectral form factor. And let me first talk a little bit about that. Now, in the free string limit, we of course know what the partition function is. And for simplicity, let me just consider Bosonic string. The story for superstring is somewhat similar, at least conceptually, qualitatively. So you consider Bosonic string in 26 dimension. And in order to have a discrete spectrum, let me focus on the case where all the spatial directions are compact. So they have some radius r. Now, the free string partition function is nothing but given by this formula. So you sum over all the mass of little excitations of the string, and this is just the partition function for that you will have for identical bosons. But a difference here is that there can be a large degeneracy factor with a given mass. Okay, so that leads to the Hexagon growth. And here I'm just being very explicit. This mass is just what you saw on the first few pages of the Pochinsky's book. It has this, the oscillator contribution, and it has the contribution from the momentum and winding in the spatial directions. Of course, in this sum, we also need to satisfy the level matching condition between the left moving modes and right moving modes. Okay. Now, what is important is that this sum is only convergent when the real part of beta is greater than the inverse Hexagon temperature. That is something that we established earlier. It's just because the asymptotic growth of the density of state is exponential. But we can analytically continue it into other region in the complex plane. Okay. So the reason that I want to discuss about this will be evident later. Now, such an analytic continuation, so analytic continue the partition function into unconvergent region is most clear if we write the free energy as a one loop partition function of a string on the thermal manifold. So that is the relation between Lorentzian and this thermal manifold that I alluded to earlier. And this is how the winding modes are derived in the first place, of course. Now, in terms of formula, it is basically saying the free energy or minus the free energy is given by a integral over some fundamental domain of SL2Z that I showed here, multiplied by an infinite sum over terms like these. And the detail doesn't really matter that much. What you need to know is that in this sum, on the exponential, there is this B alpha. And the B alpha corresponds to the mass, basically is proportional to the mass of the string modes on the thermal manifold. So in other words, here you see that on top of the contribution that you already have in the Lorentzian space-time, you had another contribution from the momentum and winding from the time direction. Of course, on this thermal manifold, you also need to satisfy the level matching condition that's enforced by the tau1 integral. And it sets C alpha to be 0. And C alpha is nothing but the level matching condition. Okay. Here, alpha labels all the quantum numbers collectively. So there are quantum numbers N, W, and the other ones. Okay. Now, we want to analytically continue the free string partition function, and we see that after the analytic, we see that it can be done by looking at this sum. Basically, when we see that this integral over tau2 is only convergent near infinity if the real part of beta B alpha is greater than 0. But once you do an analytic continuation, you could continue it into regions where the real part is negative. But in the end, you will end up with a singularity, in this case, poles in the free string partition function located at places where B alpha is equal to 0. Okay. And of course, C alpha should also be equal to 0. Otherwise, the contribution just becomes 0. So
can I ask something?
Yes.
Here, I mean, is it a pole or a branch cut?
Sorry, can you say that again? Didn't hear it.
Is it a pole or a branch cut?
Oh, it's a pole. It's a pole. So here it looks like a branch cut, but this d alpha, in this case, is always an even number. So it's always this to some integer power. So in this case, it's always poles. In more general cases, for example, if you have non-compact spatial directions, it will be branch cut in general.
And are there cases where the partition function vanishes?
In which case does the...
I mean, are there values of beta, complex beta, where the partition function vanishes?
No, it doesn't vanish. Here, I'm just saying...
no, not here. I'm saying that, I mean, if you I mean, you said it has poles, but does it also have zeros if you analytically continue beta? So do we know the analytic structure?
Yeah. Right. In the bosonic case, it's always poles. In the superstring case, there are zeros, exactly. But that's because you have fermion zero modes. And whenever, so let me maybe first talk about the interpretation of these poles.
Okay.
These poles come from, if you didn't follow this derivation, it really doesn't matter because the physical interpretation is very simple. All these singularities in the free string partition function comes from places where some of the string mode on the thermal manifold becomes massless or becomes tachyonic. For example, we know that there is a pole at the inverse Hexagon temperature. That is nothing but because of, in the target space, in this thermal manifold, the first string winding mode becomes massless. And in general, you have other string modes and they become massless in general at some other value of beta, which I denote by beta tilde here. And these are nothing but the criterion that it becomes massless, because I told you that B alpha is proportional to the mass of the string mode. Okay, so in the bosonic case, all of these string modes, they are space-time bosons, and they lead to poles in the partition function. In the superstring case, you can repeat the calculation. Now, in that case, you see that there are space-time fermions that can also become massless. And when that happens, you have fermion zero modes. And fermion zero modes will make the partition function vanish. Okay. But now, in the discussion of spectral form factor, I will the only thing that will be important are the poles rather than the zeros. We don't really care about the zeros here. The commonly known singularity, as I said, is simply the inverse Hexagon temperature. So in that case, d alpha is equal to 2 because we have two string modes. The first, the winding mode with winding number 1 and -1. And they give you a 1 divided by beta minus beta Hexagon, very close to a beta Hexagon. And this is exactly the result you expect since you have this Hexagon density of state. But an important point here is that instead of having only singularities on the real axis, like the inverse Hexagon temperature, most of the singularities or most of the poles, they locate on the complex plane, okay? So most of the beta tilde are complex numbers. So now let me come back to the question that we're interested in. What do this have to do with the spectral form factor? To see this, let's first do a simpler exercise. Let's just try to compute the density of state in this formalism, okay? Now the density of state by definition is the inverse Laplace transform of the partition function. And you integrate beta over an imaginary contour, and the real part of that contour should be greater than any singularities of your partition function. Now you integrate over this imaginary line, but now something you immediately will be tempted to do is to deform the contour leftwards. So you could deform it leftwards, but you start to pick up contributions from each of these poles. Now, obviously, this leading pole, the pole that is most to the right, namely the inverse Hexagon temperature pole, it gives you the asymptotic Hexagon density of state. But the other poles also give you contributions, and they give you contribution that goes like e to the beta tilde times e, let's say a pole at beta tilde. These are tiny corrections compared to the Hexagon growth, since all the other singularities, as you can check, have real part that is smaller than beta Hexagon. So they are very small when you have a large energy, okay? And therefore, they are usually never talked about when you consider standard thermodynamics because they are negligible in the thermodynamic discussion. On the other hand, they become important.
Can I ask about the previous thing? So you
Yes.
also seem to have another pole on the real axis, not only the Hexagon pole, but some other pole.
Yes, exactly. Yes.
But we should have seen this, right? Even in the usual density of states, we should have seen this. No.
But still, for example, this here I'm drawing here. This will be the winding mode that with winding number 2 minus 2, but has no momentum. So it will be massless at beta hexagon over 2. It is not important in the usual discussion because you see, since in the exponent you have a beta hexagon over 2 is much suppressed than the hexagon density of state. So you don't see it at high energies.
Okay. This is a subleading direction.
It's subleading, yeah.
Okay, and do you have finite number of these poles, or you have?
No, you have an infinite number of
infinite
poles.
number of these. Okay,
Yeah.
thanks.
Okay. So now let me discuss how this is related to the spectral form factor. Now the spectral form factor, it is written as this discrete sum, but one can rewrite this exactly, not just approximately, exactly in a form that looks like an inverse Laplace transform. So you also integrate over beta on this imaginary axis. But what's different from a Laplace transform is that on the exponent, you have a quadratic term of beta square, delta square. And also, since when you have a t here, in the partition function, you have a beta plus it. Okay. But still, you can do this contour deformation that I mentioned earlier. And now you see that the pole at beta theta contributes this amount to the spectral form factor. You see that it is, let me first point out the property of this. You see that this contribution, it peaks not at t equals to 0, but at t equals to the imaginary part of beta theta, okay? When t is equal to imaginary part, this is 0. And also another property is that at the peak, so when t is equal to that, you only have these two terms, and the singularities or the poles with a larger real part will give you a dominant contribution to the spectral form factor. Now, before I tell you like how to use this to understand the curve, let me make some comments. So the use of partition function in non-convergent region is a bit formal because the partition function a priori is not defined there. But this procedure is merely a way to extract some information about the spectrum or the density of state and the spectral form factor. And these quantities are completely physical. And the same answer can be derived through other ways, but this contour deformation thing that I was talking about is the simplest way to talk about it. The contributions from these other singularities, they are not important in usual thermodynamics, but they expose themselves in the spectral form factor. Now, what are the singularities in the Bosonic string theory? Ignoring the usual tachyon, which is we shouldn't really be doing that, but let me ignore that. And now the singularities in the Bosonic string will be located, like here I'm drawing a subset of the singularities. And as I mentioned earlier, since at the peak, the poles with larger real part will give you a larger contribution. We are mostly interested in the poles that are most to the right in the complex plane. So apart from this inverse Hexagon temperature, we are interested in the poles here, okay? And now let me focus on them. And they come from some winding modes that are very interesting. So as I said, this comes from the winding mode that doesn't have momentum in the time direction. But these string modes, they come from winding modes that only winds once. So winding number is only +1 or -1. But what's different is that they have momentum along the time direction. And they also have some oscillator number in the transverse directions. Okay, so they have either a n left non-zero or a n right non-zero. Okay, and the special property of this poles is that one of n right or n left is equal to 0. So you can work out where these poles are, and it's given by this simple formula. So beta is proportional to 1 plus minus I times square root of n minus 1. Okay. And now we can use this to completely understand what we saw in the numerics. Basically, as I said, they lead to peaks in the spectral form factor that locates when the time is equal to the imaginary part. So here in this dashed line, I'm drawing the prediction of these imaginary parts, and they fit nicely with each of these peaks. Okay, but you see, since all of these beta have the same real part, naively we should get an almost flat spectral form factor. The peak should have the same amplitude. But we saw that the spectral form factor is slowly rising. So why does it rise? It is very simple. It is simply the fact that as you increase time, namely increase the imaginary part, you also increase the oscillator number. As you increase the oscillator number, there is a larger and larger degeneracy of the string modes at that level. Okay, with the same oscillator, total oscillator number. And that degeneracy factor leads to this slow growth of the spectral form factor. Okay. Now, let me come back to what happens once we add back in the gravity attraction, or if we have if the energy is now comparable to 1 over G Newton. We know what happens for the early part of the curve. The early part of the curve simply turns into the Horowitz-Bosonic solution. Now, once you understand the free string picture, it's immediately almost, I think, very suggestive to say that the later part of the curve will come a family of other classical solutions that are generalizations of the Horowitz-Bosonic solution, but not of the thermoscalar winding mode, but of these other winding modes that starts to dominate the spectral form factor at later time. For each of these winding modes, you can apply the similar procedure of the Horowitz-Bosonic construction and construct the classical solution. And I expect that the later part of the curve is given by this family of other classical solutions, at least at relatively early time. So let me just tell you 2 reasons that I find this quite likely. The first reason is that we don't expect a phase transition between free string and a gravitating string gas. Physically, what happens is just the gravity attraction becomes just slightly strong enough to pull the string closer together. So qualitative feature should remain. Qualitative feature for the free string should remain in the limit where you have a little bit of gravity attraction. Now, another important reason is that the important coupling involved in finding the Horowitz-Bosonic solution is very universal. It only involves the coupling between the winding mode and the fluctuation in the size of the Euclidean circle, namely the radian, so-called radian. And it comes in the mass term, okay? For all the other string modes that I'm talking about, you will have the same type of coupling. So if you neglect anything else, the construction of the solution will be almost the same. And in the Horowitz-Bosonic solution, there are arguments that other interactions, for example, the quantity term of this chi field, are suppressed at long distances compared to this coupling to the radian. So for the same reason, I expect the similar argument to hold for the other string modes. Now, to construct the solution, we will need to fix the length of the Euclidean circle at infinity to be close to the value, to be some complex number, to be close to the value where these string modes becomes massless. And we don't expect the canonical ensemble discussion to really make sense because the the real part of that complex number will be smaller than the inverse Hexagon temperature. But it merely serves a way to construct the solution in the microcanonic example. And like the Horowitz-Polchinski solution, you could try to use the Gibbons-Hawking procedure to compute the entropy of these solutions. And they lead to exponential growth, but with a different exponent, okay, for each of these other solutions. Now, for some reason that I don't have time to go into, the Horowitz-Polchinski type approximation will break down at a time scale that scales as 1 over G string to some positive number. Okay? So we don't expect this story to hold at a very late time. And physically, we don't expect to hold to a very late time, of course, because even if you just have a little bit of interaction, what we expect is that at a very fine detail of the spectrum should start to look like somewhat random and somewhat chaotic. And the spectral form factor should start to have some property that looks like the random matrix theory. So at a much later time, something must happen, but I'm not sure what really happens. Okay. Okay, can I have 10 minutes or 15 minutes? I'm not sure how long I should go on.
Yeah, sure. 10 minutes is perfectly fine.
10 minutes, okay, yeah. So now the last comment I want to make, so let me make one more comment about the string case and just talk a little bit about the gauge theory case. So for the string case, there is this interesting discussion of the black hole string transition. So if we further increase the gravity attraction or the mass of the object, we expect the string star to eventually collapse into a black hole. Now, we could ask, since both the Horowitz-Polchinski solution and the black hole solution, they are classical solution of string theory, we could ask whether this process is a phase transition or is a smooth crossover. Questions like this. In the type 2 string theory, there is a clear argument based on computing indices that suggest that there cannot be a smooth crossover at a classical level, at the worldsheet CFT level. In the heterodyte string theory, so this was in the recent paper, our analysis is inconclusive. But nonetheless, we know that what is the correspondence of the early curve. So the early curve of the Horowitz-Polchinski solution just should turn into the black hole solution, even though there might be a phase transition in between. Now, I don't know what's the analog of the other classical solutions. There might be some black hole solutions that some analog solutions that we are missing, or for some reason, because there's a phase transition, this contribution just basically goes to 0 and you don't see it in the black hole phase. Okay, so this is just an interesting question to think more about. Okay, now the gauge theory.
You said that if you have, you are saying that you have this is due to some string modes which have momentum along the time circle. So these solutions would be rather complicated, right? Because they are some kind of I mean, they will be inhomogeneous in time and space, right? Because if you would believe,
right, but I think not necessarily, because, for example, this string mode itself might be not invariant under time translation. But for example, the square of chi and chi star might be the square might be translational invariant. So the metric itself might be translational invariant. I haven't thought about this question too much, but I agree. Yeah, it might be some.
So in principle, you can have some Euclidean version of like Geon solutions, right? I mean, some analog of that, like something that that could be homogeneous as well, right? I mean, so.
Mm-hmm. Yeah, I'm not familiar with this Geon discussion. Maybe I can check into that later. Okay. Yeah,
I see.
Yeah, but yeah, I don't have more concrete things to say about the black hole.
Right.
Now, the gauge theory discussion is in many ways analogous to the string discussion. So I will just try to summarize what I find without going into detail. So I'll try to finish in 10 minutes. So the analog, now for the analog, let's just try to understand the analog and the rest of the story will be clear. For the string, I was talking about the string winding modes, and in particular, this thermoscalar and other winding modes that become important. Now, for let's say a UN gauge theory, the analog of winding modes is the thermal holonomy and different moments of the thermal holonomy on a Euclidean manifold. So when you consider the thermodynamics of this gauge theory, you can consider the putting the theory also on a cylinder, but in a compact space. Now, the analog of winding mode is a Wilson loop that wraps the Euclidean circle. So it's what I wrote here is U is given by the exponential of integral of the time component of the gauge field. And here you can consider different moments of this thermal holonomy. So the first moment is what people often talk about is the Polyakov loop, which can be used as an order parameter for confinement, deconfinement transition. But here, as I said, in the spectral form factor for strings, there are other string modes that become important. So that naturally motivates you to consider other higher moments of the thermal holonomy. Now, a nicer way to characterize this is to look at the eigenvalues of the thermal holonomy. So this is a unitary matrix. It has n eigenvalues, which are just faces, okay? And you could look at how the angles, they are distributed on the real axis. They are distributed from 0 to 2 pi. And in the large n limit, that is given by some eigenvalue density given by this rho of theta. Now, let me not go into detail of this, but basically in the free theory, the computation is not difficult because people have pointed out that a good way to compute the thermal partition function of the free large n gauge theory is to consider a matrix model of this thermal holonomy. And we know the action explicitly. So you could try to find saddle points of that. And in the string case, I've talked about the geometries of strings. So we have this Horowitz-Polchinski solution and these generalizations of the Horowitz-Polchinski solution at a later time in the spectral form factor. So there are some analog of the well-known geometry in that case is the Horowitz-Polchinski solution that was identified in the literature before. And there, in this case also, there are some well-known geometries, namely well-known distribution, eigenvalue distribution that are known in the literature. So in the canonical example, in the free theory, with only adjoint matter, the story is very simple. So at low temperature, the eigenvalue distribution is completely uniform. So it's completely uniform from 0 to 2 pi, while as you go above the Hexagon temperature, so in the free theory, there is also a Hexagon transition. It starts to become a gapped solution like this. So by gap, I mean that the starting point of this distribution has a gap from theta equals to 0. Now, in the microcanonical example, since this is a first order transition, the transition temperature corresponds to a range of energy in the microcanonical example. So there is an intermediate range of energy where you have a cosine theta fluctuation in the eigenvalue density. So this is just saying that in the literature, people have worked out these saddle points of the Largian matrix model that I showed you earlier. Now, the upshot of this is that if you consider the spectral form factor using this saddle point, you get a fast decay, you get exponential decay, just as what we will get for the black hole or what we will get for the Horowitz-Polchinski solution. And it decays to exponential small at a time that is of order 1, okay? So you could either consider this saddle point or that saddle point. It gives you a curve like this. And as I emphasized multiple times, this is puzzling because the spectral form factor is a sum over exponentially many order 1 terms. It's surprising that it becomes exponentially small. So we expect something else to come in to save the day. Now let me jump over this. What happens is that there are other saddle points of the matrix model that you could find. And for example, one saddle point that you might encounter is a saddle point that has cosine 2 theta variation, okay? So for example, in this saddle point, if you consider the order parameters, for example, the Polyakov loop, the expectation value of trace U or the Polyakov loop is non-zero in this saddle point, but it will be 0 in this saddle point because it has a cosine 2 theta variation. On the other hand, in this saddle point, trace U square will be non-zero, while trace U square will be 0 in this saddle point. So this is just saying that this is analogous to the story that we saw in string theory, that other winding modes starts to dominate the spectral form factor at a later time. In this case, it's not winding modes, it's different moments of the thermal holonomy starts to come into play at a later time. A nicer way, okay, let me jump over this discussion and just talk about this. So a nicer way to distinguish these different saddle points is to use the symmetry principle. So you could consider what is the symmetry that these saddle points preserve. So as famously known, the early time saddle points breaks the center symmetry of the gauge theory on a thermal manifold completely. While these other saddle points that was discussed in my paper, they preserve some subgroup Cn of the center symmetry. Okay, so you can describe them by using this principle. You can distinguish them by looking at this. Okay. Now, it's easy to do the analysis in this intermediate range of the energy because when the saddle point of the matrix model is ungapped, the formula are very simple. But you could go above that. You could still go above the Hexagon temperature, Hexagon transition, and consider the gapped phase. The analog would be the early time saddle point of the thermal holonomy is given by this one gap solution. But what you can show that at later time, you can have, for example, a two-gap solution or a two-cup solution or a multi-cup solution that starts to dominate in the spectral form factor. The last comment I want to make about the gauge theory is, of course, eventually we wish to understand the gauge theory as strong coupling, because the strong coupling limit is directly related to the black holes. Now, the thermal holonomy is still a useful concept as strong coupling, of course, because it is originally proposed as an order parameter for deconfinement. Well, as Edward Witten showed, in the bulk, we also know what that means. In the bulk, we know the correspondence is just a Hawking-Page transition of between thermal ADS and black holes. Some authors in the literature have proposed effective action for the thermal holonomy as strong coupling. And they use these effective actions to successfully reproduce some qualitative features of various transitions that you find in the bulk. So we don't know the action exactly, but if you write down some effective theory, at least as these authors, they point out, it seems to make sense, reproduce many properties of the bulk. It seems that if we use this model, we will encounter some new phases in the spectral form factor, like the ones that I discussed, that I just briefly told you in the free gauge theory, okay? But it's, I think that right now it's slightly difficult to draw a concrete connection to strong coupling because there seems to be some basic questions that we haven't understood. For example, I don't think there is a concrete calculation in the bulk that one knows how to do to reproduce what is the shape of rho of theta for even a Euclidean black hole, for a large black hole. So people, like these authors, they have suggested that for a black hole, this rho theta should be more or less similar to the deconfined phase, to that in the deconfined phase of the free gauge theory. Namely, you should have a gapped solution. But I don't think there's a clear way to see that just from the bulk calculation. Okay. So it seems that we have to understand these more basic questions in order to understand the connection to strong coupling better. Now, let me just conclude. So the new saddle points that we found either in the string case or in the gauge theory case that I briefly go over, even though they are exponentially suppressed compared to the early decay, they are still very large. They are still of order e to the n square in the gauge theory language, or they are of order e to the 1 over g Newton. And if you consider fluctuations around them, they have very small fluctuations. Namely, as a function of time, they are pretty smooth. They have very little fluctuations. For the black hole, we generally don't know such contribution. And if we only know 2 ingredients in the literature for the black hole in general. We know the initial decay. We know that at later time it starts to fluctuate, and the average is given by the wormhole. But the wormhole only gives you an answer of order 1, okay? And that's why it fluctuates a lot around the order 1 number. Now, is there a simple reason that we don't have other contributions in the black hole? And in particular, if we think about the results that I show you about strings and gauge theory, we could consider the black hole string transition or turning on the 2-Hooft coupling in the gauge theory. It seems to suggest there must be some phase transition at some finite 2-Hooft coupling or some phase transition between strings and black holes, so that those new saddle points that I showed you have to disappear in the black hole phase. But unfortunately, right now, I don't have more concrete things to say about the nature of the transition. On the other hand, in ADS3, as was pointed out in this nice paper in 2016, in ADS3, we do know some family of other saddle points other than the BTZ black hole that starts to dominate at later time in the spectral form factor. So these are the SL2Z images of the BTZ black hole. But in general, in higher dimensions, for example, in ADS5, I don't know a clear way to, I don't know an analog of that. Also, in this case, I think one can go to the microcanonic example for the angular momentum. So you can set the angular momentum to be 0. Then you will get rid of these other saddle points. Okay. Now, although, as I said, it seems challenging to directly relate the gauge theory discussion to strong coupling, one can ask what happens at weak coupling. At weak coupling, at least a short time, saddles similar to what I briefly mentioned should still be a good description. Now, is there a notion of chaos that starts to emerge at longer time? And if it emerges, does that involve something completely different, or can one describe it?
So by chaos, you are meaning random matrix behavior or random matrix?
Yeah, random matrix statistics at a very fine-grained scale in the spectrum.
Okay, I see.
Yeah. So one question is that, can you gradually approach that from the discussion I showed you, or does it involve some completely different physics? So that's an interesting question to think about. Also, in the string case, as I told you, that there is some reason to believe that this other family of the Horowitz-Pochinski solution breaks down at a time that is of order 1 over G string to some positive power. What replaces that, I'm not sure. It's an interesting question whether there is a wormhole solution for the Horowitz-Pochinski type for the winding modes as well. So that is also something to think about. And finally, an interesting question that I don't have answer to is whether there is a Lorentzian dynamical interpretation of these saddle points. Note that in the string case, these winding modes are very interesting, as was mentioned earlier. They carry momentum and the oscillator number in the spatial directions. So that's what I want to say. Sorry for going over time a little bit. Thank you very much.
Well, it was a very interesting discussion. Yeah, no, I shouldn't feel sorry. Yeah. So any question? I have a question which is a very kind of not discussed by you so yet. So is there some possibility of studying some of these things also in lattices like BFS's matrix model, or say you could study similar things, for example, the gauge theory. Okay, analytic continuation may be difficult, but at least but in principle, I think now this would be acceptable to some extent.
Yeah, I think some people are doing Monte Carlo study of the BFSS matrix model. I think it's an interesting question to ask whether one can study the spectral form factor there. It's of course difficult to study that analytically because we don't know what is the action of the thermal holonomy there. So it's a bit difficult to study that directly analytically.
But people are doing such studies. Okay, I mean, not analytically, it will be hard, but on the Monte Carlo or some simulations of that kind, in principle, should.
Yeah, definitely. I think that is interesting. Yeah, I haven't thought about that before.
Okay.
For example, people, I know that people are studying what is the, since you are doing numerics, you could directly see what the thermal holonomy is, or what it looks like in the black hole phase. And I think people have achieved some preliminary result on that. But I believe it will be improved like as time goes on. It's very difficult numerical computation.
Mikael, you had a question.
Yeah, can I ask? So this last part of the talk where you discussed this Hawking page phase transition and similar calculation in Young-Mills. Actually, in recent years, there has been a lot of work in the supersymmetric case, supersymmetric Hawking page phase transition and the phase diagram of black holes. And so in that context, you think one can study the spectral form factor, and will it teach something new? What is your expectation?
Yes, that's a very interesting question. And actually, I've been thinking a little bit about that. So, but I'm not directly thinking about the spectral form factor of that. I think here, there is a question which I think one can possibly resolve in that context. As I said, we don't know what is the shape of rho theta for a Euclidean black hole. And we don't know how to do a bulk calculation to see that. But as you mentioned, in recent years, there have been people using this kind of matrix model to study the index of BPS black holes. In that case, people do find in the black hole phase, for the supersymmetric black holes, the eigenvalue distribution, rho theta, is a gapped solution. So I think it would be very interesting to understand in those supersymmetric setup whether you can compute this from the bulk, whether there is a way to compute from the bulk. This is a concrete thing that I'm interested in those setup. But of course, yeah, one could also ask whether it's interesting to look at the spectral form factor. But I would expect, since it's BPS black holes, the only parameter would be these charges of the black hole, and you will be discussing a spectral form factor in terms of the charges. I think it would be more or less like similar to the free theory. Like,
so in these BPS black hole discussion, there is a useful notion of temperature also. And I mean, with respect to this notion of temperature, people study the Hawking page phase transition. So it seems likely that there is a notion of beta, and hence perhaps.
Yeah, I think what you're referring to is some in those discussions they tune some chemical potential, and that takes the role of beta. And in general, they also tune the chemical potential to complex numbers.
Yeah.
But I guess I'm just saying that if you really think about the spectrum of the BPS black holes, they are described by these charges, and charges obviously they satisfy quantization conditions. So you don't expect to see random matrix statistics in that. So in that sense, it's not a lot more interesting than the free theory, because more or less the spectrum look like those of free theory. But still, it might be I'm missing something interesting. Yeah, it might be interesting to study that. I'm not sure.
Okay. Thank you.
So I think we have this time now to thank you again for this brilliant seminar and for this very exciting work that you have shared. So good, you should visit us in Chennai at some point, and it will be good to have you here.
Okay,
And,
thank you very much.
So please send the slides. I will send you to me because
Oh,
I'll
yeah,
upload
I
it.
can,
Yeah, thanks.
I can send you the, yes. Okay.
Yeah.
Okay, see you.
Okay, so see you then. Have a nice day. Bye.
You too.